Hey guys, this is Mr. Galoy again. Hey, we're back on this graphing practice packet here. A couple days ago we did the direct relationship. That's where we get a line. And then we did this inverse relationship. On this sort of relationship we get a kind of a hyperbola. As one of the variables goes up, the other goes down. We said we could turn that into a line, but we had to take a reciprocal. Well, we're going to kind of focus in on the last couple of the sheets, and these are our graphs called parabolas, or they're called parabolic graphs. And we really have a couple of types of parabolas, and I think you probably know what a parabola is from math, but a parabola kind of is something that kind of looks like this. This is what's called a top opening parabola. You know, we also can deal with the bottom opening parabola, and we also have what are called side opening parabolas. Generally, in a physics class, we won't see the complete parabola, but we'll only see kind of part of it, and I'll give you an example of that. With a top opening or bottom opening parabola, we have that our y variable is directly proportional to the square of our x variable, and for a side opening parabola we have just kind of the opposite, that y squared is directly proportional to x. So we see these types of graphs pretty common in physics, so you need to be able to kind of deal with this also. These types of graphs are called parabolic relationships. So here's again my data. Casey wants to determine, again, Casey's my older son, he wants to determine if there's a relationship between the time it takes for the object to fall and how far above the ground it's dropped. This is a concept called free fall. We drop in an object and we'd like to figure out then things about that object as it falls. In this case, we'd like to maybe investigate the time it takes for that object to fall. So again, this is our x variable. We're going to write x there, and we'll write y there. This is our y variable. So this will be time. And we've got units called the second there. That's our typical time unit. And this, we have our distance. We're going to put that in meters. Now, it looks like the time goes up to maybe about 4 seconds. So we could maybe do 0, 1, 2, 3, 4. That would work when we grid this out. Distance, we need to take it up to a little more than 24. So I think we can go maybe by threesies. 3, 6, 9, 12, 15, 18, 21, 24, and 27. That looks pretty good. So let's put in our points. 0.5, 0.5, 1, 2, 1.5, 4.5, 2, 8, 2.5, 12.5, 3, 18, and 3.5, 24.5. Now notice we don't get a line. We get this sort of shape here. There's your, so this is basically kind of just one lobe of a top opening parabola. Do you see kind of what's going on there? So we're saying that y is directly proportional really to the square of x, or in this case our distance, d, distance, is directly proportional to the square of time. Now the question is, can we actually get a slope here? Well, a parabola doesn't have one slope, right? Its slope is constantly changing. So we can't really get, we can't really use y equals mx plus b on it. That's what makes quadratics and parabolas a little bit more challenging. Well, is there a way really to turn this graph into kind of a line? Well, there is, but again, we have to do something to the data. Well, on the previous page, with inverse relationships, we were able to take the reciprocals of this data and turn it into a line. We can't use reciprocals now, but here's really the key right here. You see, that's x squared. So what we can do then is take our x data and we can square that. So really what we want then is times squared. So we can take 0.5 and square it. So you got a calculator in front of you. So just take 0.5 and square it. We get 0.25. Take 1 and square it. We get 1. Take 1.5 and square it. We get 2.25. Take 2 and square it. We get 4. So that represents the first 4 points, and that's honestly probably enough to get us going here on this graph. So on this graph, we're going to now write x squared, so that's going to be times squared. That'll be in units seconds squared. And we'll write distance. Again, this won't change here. That'll be meters. That's our y data. So again, we kind of did by threesies here. We can do by threesies again. Okay, and looks like we'll need to start at 0, but we'll need to go up to maybe 4 here. So we can again kind of use what we did last time. So 0.25, 0.5. 1, 2. 2.25, 4.5. 4.8. You see, basically what we've done is we've taken this curved shape, what we call a parabola, and we've converted it into a line. Again, why do we want to do this? Well, we want to do this because if this is really linear, we can use y equals mx plus b. Okay? Our y variable represents distance. Then we have the slope. And our x idea then represents time squared. And we have the intercept. But look at b here. It looks like it goes through the origin, so we can make that term go away. Well, we'd like to now get the slope of that. And one of our points would be 0, 0. The other point then would be 4, 8. So our slope, again, remember, is y2 minus y1 over x2 minus x1. So 8 minus 0 over 4 minus 0. The units here would be meters over second squared. And so our slope then is 2 meters per second squared. That then can be placed into this. We get distance then, let me make sure you can see that, distance equals 2 meters per second squared times t squared. Now, there's your equation. Again, what good is it to have that equation? Well, if I know then time or different values of time, I can find the distance. So maybe t is 5. So 5 squared, 25, times 2 is 50. So in 5 seconds, the object would have fallen 50 meters. Now, we also have a second type of parabola, and this would be page 4 here. We have a second type of parabola, and we're going to find out that this represents really a side opening parabola. So here's what we got. Ryan drops an object from a certain height above the ground and measures its velocity. So that velocity means the speed. So here's his data. So again, this represents the x data. That'll be height. That's in meters, and this represents the velocity. Meters per second. All right, so what we want to do is, looks like the height, we need to go from 0 up to about 4. Okay, and it looks like for velocity we need to go up to maybe 8, so I'm going to go by onesies there. Okay, I think what I'll do is I'll pull out a different color so we can have a different color on this one. So 0.1, 1.4. 0.25, 2.2. 0.5, 3.2. 1, 4.5. 1.5, 5.5. 2, 6.3. You see what we're getting here? You see this type of graph? 2.5, 7.1. 3, 7.7. And 3.5, 8.4. You see kind of what we're getting? We're getting something that kind of looks like this, okay? See, that kind of looks like that. That's, you know, for a full side opening parabola, we'd have both lobes, but we don't have the bottom part. We just have the positive numbers. So we'd basically say that y squared is proportional to x, or you could say y is proportional to the square root of x. You could say either one of those. All right, does that make sense? But again, we don't have one slope. Okay, so we got to find a way of linearizing this. Well, in the previous parabola, we squared the x data. So now what we're going to do is square the velocity, the y data. So we want v squared there. So we're going to take all these numbers and square it. So we won't do all of them, but we can do maybe the first 4 or 5. So we want to square 1.4, we get 1.96. We want to square 2.2, get 4.84. We want to square 3.2, 10.24. And we can square 4.5, 20.25. Okay, that makes sense? We're just taking these numbers and squaring them. Again, we don't really have to do all of them. I'm just going to do the first 4 here. So our height, this is our x data. Our height didn't change. So we can put 0, 1, 2, 3, 4. Our velocity now is squared, so we'll put velocity squared. And that's going to square the units, so we're going to have meters squared over seconds squared. And it looks like we need to go up to maybe about 20 or so. So 2, 4, 6, 8, 10, 12. So I think I can do by twosies. 14, 16, 18, 20. So we'd have 0.1, 1.96. 0.1, 1.96. So that's somewhere around here. We have 0.25, 4.84. 0.25, 4.84. 0.5, 10, 0.24. You see, we're now turning this into a line, aren't we? 1, 20.25. Okay, you see, you make a line here. Again, why do we want to make a line? Well, if we make a line, then we can use y equals mx plus b. Okay, makes our math a little bit easier, right? Our y data represent velocity squared. Velocity squared. That equals to our slope times our x data, but our x data is height. Look, it looks like we go through the origin, right? So we can make that term go away. So we've got 0, 0 for 1 point, and this point was 1, 20.25, right? So our slope, I hope you're doing okay with slope now, that's going to be 20.25 minus 0 over 1 minus 0. That's going to be then meters squared seconds squared over meters. Okay, there's my units. So the slope is then 20.25, right? That'll go in here. So we have v squared equals 20.25 meters squared seconds squared over meters times our h. Okay? That represents a side opening parabola. So let's take a step back here. We've got four basic types of graphs. The easiest one to deal with is a direct relation. We get a line. Okay? We can get the equation. We can find the slope. Why do we want the equation? Well, we can predict then numbers and things. Okay? We have an inverse or indirect relationship. We get a hyperbola. Again, we don't really like hyperbolas. I mean, they're nice, but we really don't like them. The x data to do that. Well, we have two different types of parabolas. We have top opening parabolas that we deal with quite a bit. Okay, we get this parabola, this curve shape. Again, can't get one slope. So we're going to linearize this, turn it into a line by squaring the x data. Okay, we can then get the equation. Finally, then, we've got this side opening parabola. In this case, we have to square the y data. All right? So those are the basic types of graphs we see, and we're going to be kind of practicing those over the course of the next few days. Excellent work, guys. We'll talk to you later. Bye.